Hello everybody. Today's lesson is about applications to the derivative. A lot of times in math people wonder why is it that we actually learn this stuff, and a lot of it is because it develops a certain part of your brain that no other subject develops, and it's a logical subject, it's proof oriented, it's very logical, and so in and of itself it's worth studying. But there actually are practical applications to mathematics. There's a lot of uses for it. And so today we're going to take a look at some very basic applications to derivatives and when you would use this kind of in real life, although the situations we'll talk about you might argue are not real life situations. But still, they're situations that use calculus in their solutions. Okay? So we're going to be covering section 3-4, looking at some basic applications for derivatives. So the first example I want to give you has to do with, just in general, a rate of change. Now we've used rate of change in different situations before. It's synonymous with slope. We've talked about the connection with velocity. But rate of change basically is anything that changes. Rate of change is how fast it changes. Okay. So any application where you have a quantity that's changing, calculus is applicable. So let's look at a situation where we actually have a cylinder. And in this problem, let's say the cylinder's height is equal to its diameter. Okay? So that means if I call this r for the radius, then the diameter of the circle or the circular base would be 2r. So let's just say in this particular problem that the height is also 2r. Okay, r and 2r. All right. Now here's the problem. We want to write a formula for the volume of the cylinder with respect to its radius. Okay, and we're going to actually analyze the rate of change if the one dimension were to change somehow. Okay. So first of all, we know the volume of the cylinder is pi r squared h. Okay, if that's not a formula you know already, that's something you should memorize. The AP exam will probably make reference to this formula for cylinders as well as the one for spheres and also simple basic geometric objects. Now, since in this particular problem we are given the fact that the height is twice the radius, I can substitute h with the expression 2r. So, and then I can combine terms. So the volume expression would be 2 pi r cubed. Okay. So at this point in the year, we actually have to work with, in terms of calculus, we have to work with problems that only have one variable in them. So whenever we're given a function with more than one variable, like here pi r squared h, as the r and the h are the variables, we need to be given some other kind of information to substitute out. In this case, the information was that the height was twice the radius, or that the height was equal to the diameter, same difference. So anyway, now we have a formula for the volume of the cylinder in terms of its radius. Okay? So let's say that we want to actually find an expression for the rate of change of the volume with respect to the radius. So if this were to change size, okay, the radius were to change at a certain rate, could we write a formula for the rate of change of volume? Okay, so because if the radius does increase, obviously in this case the volume will increase as well. But there's going to be a relationship between the speed at which r increases and the speed at which the velocity increases, which we'll get into a little bit later. Okay, so the next problem is, if that's the volume, 2 pi r cubed, I can write an expression for the derivative of volume with respect to radius. Okay? And I'm going to call that dv dr. Now dv dr is kind of like dy dx. It's just instead of y equals a function of x, we have v equals a function of r. So you could write dv dr, you could also write v prime, it means the same thing. But usually when you're dealing with a variable different than x, you write it like this, so that you are making very clear what the variable is. What's the variable? The function, and with respect to what variable? Okay? So we call that dV/dr, but it's the derivative of volume with respect to radius. That's how we'd say that. So then this derivative is just a matter of finding the derivative of this expression with the power rule, treating r like the variable, or the x. So 2 pi is a constant, so I would take 3 times 2 pi, which would give me 6 pi, lower the power by 1, r squared. So 6 pi r squared would be the derivative of volume, okay, or the rate of change of volume with respect to the radius. Okay. So we could actually then be given different values to plug in. What is the rate of change of the radius, or the volume with respect to radius, when the radius is equal to 2? Then all we have to do is plug in 2 for r. So dV/dr would be 6 pi times 2 squared. So that's 4 times 6 is 24, so 24 pi would be the units. Okay? Now let's go back to the beginning. Let's say that r was in inches. If r is in inches, then the volume formula would then be in cubic inches. If the volume is in cubic inches, the rate of change of volume with respect to r, since we're taking the change in V divided by the change in r, the units of this problem are going to be units of volume per units of radius, which is going to be units of volume, which is cubic inches, per units of radius, which is inch. Okay. So although it's kind of weird to say it, this 24 pi, the units on the answer would be cubic inches per inch. And that would be the rate of change, which means for every inch that the radius changes, the volume will change by 24 pi cubic inches. Okay. So cubic inches per inch would be the correct units in this particular problem. Okay? So this is one particular problem in general that deals with rate of change. Let's look at another one, a little bit more common application, which is velocity. We've dealt with velocity quite a bit. Now velocity is a rate of change. If you're given a function for an object's position, then the rate of change of that position as a function of time is going to be called velocity. Okay, so it's just a rate of change. Now I have to define some different terms to make sure we're on the same page about this. For those of you who haven't taken physics, I need to define the word displacement for you. Displacement is similar to distance. However, displacement and velocity kind of also have a direction. We're not talking about necessarily one-dimensional direction. We're talking about direction that can be in different planes. So displacement basically is this. Let's say I start right here. And let's just say it's at 0. And if I move this way out to, let's say, 5 feet, and then I turn around and I come back and go over to here to negative 5 feet, or 5 feet the other direction, then my displacement would actually be negative 5. And the displacement is basically how far do you go, or where do you end up relative to where you start. So if I start at 0 and go this way for 5 feet, and then come back and go all the way out to here, I end up 5 feet to the left of where I started. So the negative basically is directional, it means left. Whereas positive 5 means to the right. Okay, so that's one thing about displacement is positive displacement is generally to the right, negative displacement is generally to the left. Okay? Now, that's different than distance traveled. Because if you're just, like, if you had an odometer or a pedometer or whatever, and you're keeping track of the distance that you went, it would start here at 0, and then it would go out to here, and then it would come back to here,